Okay, welcome to part 2 of this video in which we introduce the analysis of trusses. In part 1, we introduced the idea of a truss. We showed how to model a truss in terms of members that are pinned together with frictionless pins. And we did a free body diagram of the entire truss to find the reactions of the supports. Okay, and so in this part we will go ahead and draw free body diagrams at pins, and we'll use these free body diagrams at pins to actually solve for the tensions in the different members of the truss. So let's begin with this point A. Let's call this pin A, and draw a free body diagram of pin A. Okay, so we have the point that the forces act on. We have the vertical force, the reaction force, FAY, which we know from our computation using the free body diagram of the entire structure is 4,000 pounds. We have the force applied to pin A by we'll go back and actually show you. We have the force applied by pin A at this point by this member that goes from A to D. So we'll call that force TAD. We also here will have a force applied to the pin by the member that goes from A to B, and we'll call this guy TAB. Okay, and in fact, in this video at least, we'll identify the members by the two letters that identify the pins they're between. So this will be member AD, AB, BC, DC, and BD. Okay, so let's go back and complete our free body diagram. Okay, so we have TAD, and we also have then going off in this direction TAB. And we know from the structure the angle here is 26.6 degrees. Okay, well, so now we can apply the summation of forces in the x direction is 0, and the summation of forces in the y direction is 0 to get equations that relate TAD, TAB, and FA. Again, we know FA, this is equal to 4,000 pounds. And so we'll have two equations and two unknowns, so we should then be able to use these two equations and two unknowns to solve for TAB and TAD. Okay, so let's start with the summation. Oh, I guess we'll do it down here. The summation of forces in the x direction is equal to 0. Let's see, we have TAD in the positive x direction, plus we'll have the component of TAB in the x direction. And you can see if I have TAB being this length, and I've got a right triangle here, the x component of that is going to be TAB times cosine of 26.6 degrees, and this has to equal 0. Okay, so that's the sum of forces in the x direction. The sum of forces in the y direction, that also has to equal 0. Well, I have 4,000 pounds, which is FAY, and then I have plus TAB, and the component in the vertical direction is going to be TAB sine 26.6 degrees, and that's equal to 0. And now I can solve this equation for TAB. I'll have TAB, I take this guy, put it over here, then divide by this guy, and I have TAB is equal to minus 4,000 pounds over sine of 26.6 degrees, which, when I work this out, is minus 8,933 pounds. Okay, so this gives me TAB. Now I can take this value and plug it into here and get another equation for TAD. If I do that without showing all the steps, I have TAD is equal to minus TAB cosine 26.6 degrees. I take this guy, plug it in for TAB, multiply it by cosine 26.6, and I get then that TAD is 7,988 pounds. Okay, so we've made good progress. We now know TAD and TAB. Let's go back to our other window here to write down what we know. We know that TAD is, this guy is 7,988 pounds. We know TAB is minus 8,933 pounds. And I guess we can say we knew that FAY was 4,000 pounds, as well as FCY. Okay, well, that was fun. Let's now do the free body diagram of pin B. So let's go back to our worksheet, make it all go away, and draw a free body diagram of pin B. Okay, pin B has TAB, TBD, and TBC. And we know that the angle between these vectors and the horizontal for both of these is 26.6 degrees. Okay, well, we can just go about solving this. The sum of forces in the x direction is equal to 0. This says then that TAB, and this would be negative because it's going to the left, times the cosine of 26.6 degrees. I'm taking TAB and I'm projecting it onto this horizontal axis. So I take the magnitude TAB, multiply it by the cosine of 26.6 degrees, plus TBC, and again we're going to project this onto the x-axis. So this will be cosine of 26.6 degrees, and this is equal to 0, which tells us then that TAB is equal to TBC, or that TBC is equal to whatever TAB is, which, if I remember correctly, is minus 8,933 pounds. Okay, so that's what we got from the F direction. Let's look at the sum of forces in the Y direction. That will be minus TAB sine 26.6 degrees. I'm now finding this component. Minus TBC sine 26.6 degrees. Finding this component. Minus TBD. Okay, I know that, and this is equal to 0, I know that TBC is given by this, and because TAB and TBC are equal, it also shows up here, so I can solve this for TBD and discover after I take these two guys, put them on the other side, and take care of the negative signs, then multiply everything by sine of 22.6, I get TBD is equal to 8,000 pounds. Okay, so let's go write this down on our free body diagram. Okay, so we have this guy here. TBD is 8,000 pounds. Here we'll actually draw this correctly. We have TBD. We still have TAB, TBC. Okay, so we know that TAB is minus 8,933 pounds. That's the same as TBC, so this is minus 8,933 pounds. So we now know everything except TDC. And so we need to do a free body diagram at either pin D or pin C. You can choose either one, and we'll choose D because it turns out it's slightly easier. Okay, so let's go clear up our workspace again. And we have then the free body diagram of pin D. We have TBD going straight up. We have the weight 8,000 pounds going straight down. We have TAD going to the left. And we have TCD going to the right. And if we use the sum of forces in the x direction is equal to 0, that gives us that minus TAD is equal to T, whoops, got ahead of myself there, plus TCD is equal to 0, which says that TAD is equal to TCD. Okay, and there's no point in solving this in the y direction because we already know what TBD is. And in fact, if we had used point D or pin D, we could have gotten TBD more easily than we did using pin C, or I'm sorry, using pin B. Okay, so let's go add this to our picture. And okay, so we have whoops, wrong direction. TDC, this is TAD, TDC, and we had that TDC was the same as TAD, which is 7,988 pounds. Okay, so we're pretty much done. We found the tensions in each of the members of the truss. So one last comment, and then we will truly be done. The positive tensions, say this guy TAD, TBD, and TDC, positive tensions correspond, the way we've drawn this, to members that are being pulled apart. They're under tension. So I'll draw these members in hot pink. Okay, so the members with positive tensions are being pulled apart. Another way of looking at it is they're pulling on the pins at either end. They're stretched. Okay. Members that are under compression, let's see, use a nice dark blue. If I get a negative tension, that means that my members are pushing on the pins. So members that are under compression are this guy and this guy. Okay, these members are pushing on the pins. And so you can see what happens is I have a load that pulls down in this direction. That puts this member under tension. That pulls pin B downwards, which compresses member BC and member AB. Okay, so that pretty much concludes this introduction to analyzing trusses. I hope this has been helpful, and it's been most enjoyable.